watch this. If we come in here and insert a -2, we better get what? Help me. We better get -10 as an output, shouldn't we? So if you put -2 in here, look what happens. Cube root of 0 minus 10, and what do you get? -10. There's that important point. There's that important point. Okay? Let's try something else. Let's use algebra. Let's use algebra to locate the zero that we saw in the sketch. So what do I do to find zeros on a function? We put y equal to 0, don't we? Y is our f of x value, so we make that equal to 0. Right? Everybody feeling good? Now this takes you back actually to intermediate algebra. And now how are you going to solve this thing? How are you going to solve this? You have to isolate this x, don't you? Now you've all had a year of algebra already. You should be helping me on this, okay? We're going to kick the -10 over to the other side, aren't we? We're going to divide by -4. In other words, we're going to isolate the cube root, aren't we? We're going to isolate the cube root. So the cube root of x plus 2, we get that isolated as our first step to solve this, is going to be 10 divided by -4, isn't it? When you move that -10 to the other side, it becomes +10, and you divide by -4 both sides to isolate the cube root. And then do we leave the 10 over -4 like that? No, we always reduce fractions if possible. So we reduce this fraction to the common factor, 2 times 5, and a -2 times a +2, and we lose the +2 factors, and we end up with -5 halves. So we have the cube root of x plus 2 is equal to -5 halves. This is called a cube root equation. How do you solve for x in here?
You have to take it out of the cube root.
How do you get rid of the cube root?
You cube both sides.
Don't we cube both sides of the equation to get rid of the cube root? So let's come up over here. So we're now going to cube the cube root. And we have to do this to both sides of the equation. Let me back you up to something more familiar from your basic algebra background. What if you had square root of x equals 7? What do you do to both sides to solve that? You square both sides, don't you? Aren't you undoing the square root by squaring both sides? Yeah, and you get x equals 49 out of that. Okay? We're doing the same kind of a thing here. We isolate the cube root, and then we undo the cube root process by cubing. The formal name in mathematics for that is called applying the inverse to both sides. Later in the course, we'll talk about that. So when we do this, we get x plus 2. We have released the thing we're looking for from that thing that was holding on to it. And over on the right side, we get negative cubed is still negative, isn't it? Negative. And you cube 5 and you get 125 over 8. And then move the 2 over to the other side. And now, I'm solving for the exact 0, aren't I? I'm solving for the exact value of the 0, where the x-intercept is. And so now we're back to arithmetic. We need a common denominator. So we know the common denominator clearly to add these two numbers together is an 8. So we have to apply, we need an 8 denominator here, so we have to apply to both the numerator and the denominator of 1, we have to apply a factor of 8. So what we're going to do then is we're going to take 16 away from minus 125, and what does that give us? 125 and a minus 16 is negative 141, isn't it? So we get negative 141 divided by the denominator 8. That is a what? What's it called? It's a fraction, that's good. Okay. It's a 0, isn't it? Isn't this the 0 of the function? So minus 141 over 8 comma 0 is a point on the graph. How do we check that, folks? We don't look in the back of the book because this problem didn't come out of the book, did it? Okay, so what we do is we turn our calculator on. Let's come back to the screen. Here's the picture. And so what we do, we're still in the trace mode. And now we're going to punch in negative 141 divided by 8. And we're hoping for what? When I hit enter.
0.
We're hoping for 0. And there it is, folks. The precise, you can see the precise y value being 0 there. Feel good? Okay. So what we've done is we've taken a transform problem, and I've explained to you the background of why the transforms do what they do using these two examples. We did a parabola, and then we did more detail here with this cube root function, and you can see how they behave. Okay. So let's leave the transform subject for the moment, and I also showed you how to use your calculator effectively. One final thing with your calculator is what you want to do on that, and I'm going to go ahead and erase part of this work. Is one thing you also want to include in your work is then a sketch including the viewing window, which I believe that we used a negative 30 because the scaling marks up there were 5s, I believe. I think we had minus 30 on the left, looks like 10 on the right, minus 20 and top, minus 20 and 20. And then the axes look something like this. And then the quick sketch where it goes off the screen, where it has its zeros, where interesting points might be, and where the y-intercept is, and where it goes off the screen. And then you can quickly come in and sketch that thing roughly like this, and you can label a few of those important points. Like that. And the y-intercept, did I ever do that? I don't think I ever did it, but you can look at the original function and put x equals 0 in, x equals 0 into it, and that would give you negative 4 times the cube root of 2, right, minus 10. And that value is not going to be exact. This is the exact reading. The approximate reading with your calculator, without having to jump to the, you don't have to jump to the screen there. You can just put a 0 in. It's minus 15.0397. 15.0397. There's your y-intercept, folks. This point right here. Okay, so that gives you a pretty good summary of the concepts involved here at this level using transformations. Okay, let's change topics now. Let's talk about modeling. doing some real world type of stuff. In our book, I believe we're here in section 2.6 on building math models, and let's look in the textbook, and you can go to, with your Math Excel, you can go to the study plan, and you can go to this section in the book and find problems in the database on the computer system that match many of the problems that you see here. And so why don't we take, is number 7 in your homework? Anybody know? 2.6? No, it's not. Okay, so look at number 7 here, and let me enlarge that a little bit so that we can see it clearly on the screen. Here it is. Here's a picture. If you carefully read the words, a rectangle has one corner in the quadrant, in the first quadrant, of the graph of y equals negative 16 minus x squared. And another point at the origin. And so those are corners of a rectangle. In other words, we're going to be on the graph at some location x, y. Let me try to get my pen here so it's not in the writing. We're going to be at a point x, y on the graph of the quadratic function shown. And the other corner of the rectangle is going to be at the origin. And then they ask us to build some equations associated with that. Build some equations associated with that. So let's go up on the board now and talk about this. Modeling. And so this is a simple example. So we have a function given to us, y equals 16 minus x squared. Now what you should realize from our transform background is this is the equation minus x squared plus 16. What you should be able to see now, based on our past discussion, is that this is an upside down parabola, turned upside down because of the negative. Everybody feel good? And then what are we doing with the 16 here? We're adding 16 to the y values, right? So this is going to then kick it up 16. So we end up with a picture they showed us in the book. But you should be able to do this. If they just gave you this equation, you should be able to sketch this thing. So we have a picture of a parabola up here looking like that. With a vertex up here at 0, 16, and it opens downward. While we're at it, what's the x-intercept, folks? If you wanted to find the 0 here, if you wanted to find this 0, (16 to the right? Let's try it. If you put 16 in here, do you get 0 for y? If you put 16 in for x, do you get 0 for y? Ah, 4. Okay. So what you're doing to find that 0 is you're letting y equal 0. Kick the negative x squared to the other side, and you get x equals what? When you undo the squaring process by square rooting, you get plus or minus. Very good. Plus or minus 4, don't you? So you get a 0 over here, and there's also 1 over here. Right? Okay. Now, the modeling that they ask us to do with this problem is they said, we want to lay a rectangle inside the first quadrant. Here's our first quadrant. We want to lay a rectangle in here that touches the graph at location XY, and it has one corner there, and the other corner, it says, is at the origin. So if I build a rectangle that has this point as a corner and this point as a corner, then I have to build it looking like that, don't I? What's this x value right here? I answered it already. What is this x value here? X, okay. How tall is this thing right here? Y tall, right? Or isn't it 16 minus x squared tall? Isn't that the height? And isn't this the base? Feel good? So let's see if we can write an equation now, a model that describes the area of that rectangle. The area of that rectangle. You know from your pre-algebra background that a rectangle has area base times height. The area equals base times height, and the base happens to be x, and the height happens to be 16 minus x squared. Feel good? Everybody happy? Okay. And so this is an area formula for the rectangle, is it not? For different values of x. For different values of x. Area of the rectangle. All right. Is there a restriction, folks, on the domain of this model? Is there a restriction on the domain? Has to be positive, because otherwise we wouldn't have a rectangle if we had some negative base, right? So you got to have positive x. Any other restrictions? Has to be bigger than 0. And in the back? 4. Can't be any bigger than 4, can it? So doesn't the area of this rectangle have to be trapped in a domain where x is greater than 0? Here's your domain, and less than 4. Otherwise, you wouldn't have a rectangle. Otherwise, you would not have a rectangle. If this thing was out here near 4, what if the base was out here near 4? Wouldn't it look something like that? Very flat. And what if the base was very small, like near 0? Wouldn't it look something like this? If I could draw well, right? And as you get close to 0, what's the area turn into? 0. And if the base gets near 4, the area turns back towards 0 again, doesn't it? Okay. What kind of a polynomial is this? See it? You all see it? Isn't this, I'm going to leave a little space for a reason. If I multiply this out, isn't this a negative x cubed plus 16x? If you multiply this x times this binomial, right? Okay, so now what we want to do is we've built a model for the area of the rectangle for variable base length, variable length of the base. And what we want to do is to draw a sketch of this. Can we factor this thing shown here anymore?
That's a difference of squares.
Ah, a square minus b square. We talked about that a while ago. This is a 4 minus x times a 4 plus x, isn't it? Okay, so we could factor this thing some more. And so this is called the factored form. This is the factored form. This is called the general form. Okay. All right? So let's draw a quick picture of this. What would be the zeros of this function? Here's a cubic function, folks. What would be the zeros? X equals what? 0 would turn this into 0, wouldn't it? And if x equals 4, we have a 0, and also over at negative 4. This is a cubic. Isn't it an upside down cubic? Go back to your library. It's an upside down cubic. So instead of doing the usual cubic thing, like my hand's waving, okay, it's upside down, which means it goes up left and comes down right. Looking like this. Up left, down right in its behavior. We're going to study these in more detail later. Now, what portion of the domain is good for this model? What portion of the domain? Here's a picture of the whole thing. But this is not good for the model. Just this. Just that, isn't it? Just that. So just that portion of the domain is physically available to us, and this is really a hole in the graph because of our restricted domain up here. Okay, now here's what's really exciting about this. What choice of x? What choice of x will give us the biggest area rectangle inside here? 4 makes 0. You're guessing that this is a parabola. Is that a parabola? No? Okay. So somewhere between 0 and 4 is the location where you're going to get the maximum area, right? The maximum area. And how much time do I have? About a minute. And we've got our fancy graphing calculator, don't we? So let's jump back to the calculator real quick. And I think I have enough time to do this. Let's get the answer before we finish here. And time is running out. Here we go. And I have to kick this function into here real quickly. So it's going to be x times the quantity 16 minus x squared. I'm going to set a viewing window based on what we just talked about. Minus 2 to 5, 1. And then say, oh, how about minus 10 to say 20? That may not be too good. And let's try 5 on that, see what I get. Shoots off the top. I don't like it. What I'm going to do is make my window a little higher. Let's make it 30. Now I'm going to jump to my calculate features to go maximum. Calculate, go to maximum feature, number 4. Lower value, maybe 10. Whoops, sorry. Did something wrong. Calculate, maximum, number 4. Left bound, didn't I say 5, 10, 15? Yeah. 10 I think should work. What's wrong? Excuse me? Let me go back to it. Shouldn't this be 5, 10, 15, 20? Hold it.
Why don't you just arrow over?
Oh, I'm sorry. My scaling was wrong. I had a scale of 1 there, so I had an unreasonable value. So back to this. How much? I'm going to do it. We're going to make it. Here we go. So I'm going to use a 2, and I'm going to use a 3 for my left and right. See the arrows? And I'm going to guess 2.5. And there we go, folks. The maximum area, enclosed area, occurs when the base is 2.309 and the maximum area value is 24.63. So that would be how you optimize to come up with the largest enclosed area underneath that parabola. And I think we're out of time. So that'll do it for today. And your homework quiz, I'm going to let you take until Tuesday at 10 a.m. to do that. And I haven't built it yet. I'm going to do it right now, and it'll be available. It'll be available to you starting at noon.